Settle in and let your breathing slow just a little. Imagine you are drifting in open space where the cold is not dramatic, just efficient, quietly drying every exposed thought you ever had about comfort. Ahead of you, there is a patch of sky that looks oddly unfinished, as if the stars simply forgot to show up. You might think a black hole would announce itself like a monster. It does not. It is more like a place where back stops meaning anything. Tonight, with the sleepless scientist murmuring in the dark, you will fall gently through what gravity really is and why the universe does not need teeth to swallow you. You keep drifting, and the first strange detail is how calm everything looks. Space does not hiss or howl because there is no air to carry sound. It just sits there like an empty warehouse, letting you do the panicking. That missing patch of stars ahead of you is not a curtain. It is not smoke. It is not a hole punched through the universe by a careless god. It is something more boring than that, which is always how reality hurts you. The dark spot is a region where light does not come back, not because light is tired, but because the geometry of space has been bent into a one-way slope. And right away, you may notice a common misunderstanding trying to climb into your mind. You may picture the black hole as a vacuum cleaner with ambition, a cosmic drain, sucking everything in with angry slurping noises. But that is not how gravity behaves. Gravity is not a mouth. Gravity is not a hand reaching out. Gravity is you falling, because the floor has been replaced with a curve. You are not being pulled through space so much as you are following the only straight path left. Far from this dark spot, if you had a decent view and a stable platform, you could orbit it. You could treat it like any other object with mass. You could do the same dull math that guides satellites around Earth. And that is the first insult. From a safe distance, a black hole is ordinary. If the sun were replaced by a black hole of the same mass, the planets would keep going. They would not spiral inward dramatically. They would not get vacuumed up like crumbs. They would keep circling, faithful and unaware, because gravity at a distance depends on mass, not personality. The black hole would not glow. It would not warm you. It would simply be a heavier and less helpful neighbor. You drift closer anyway, because tonight you are the curious kind of doomed. The cold stays efficient. Your skin, if it were exposed, would try to lose heat by radiation. Your breath, if you had one out here, would be impossible because there is nothing to breathe, and your body would have a more immediate issue. In vacuum, fluids do not boil because they are hot. They boil because there is no pressure holding them down. Congratulations. The moisture on your eyes and tongue would start to bubble. Not violently, not like a movie, more like the universe quietly removing the idea of comfort from your tissues. But you are not exposed. Not tonight. Tonight, you have a suit or a ship, or at least the mercy of imagination. So you can spend your attention on the dark spot. At first, it does not look like a hole at all. It looks like someone erased the background. No stars, no faint dust, just absence. What you are really seeing is the black hole's shadow, the region of sky where light paths get bent and stolen. Photons, those tiny packets of electromagnetic energy, approach the wrong neighborhood and do not leave. And it is worth lingering on that because the phrase black hole can make you picture a thing, a ball, a pit, a black marble floating in space. But it is not a thing in the normal sense. It is a place where certain exits are removed. A black hole is a region of space-time where gravity wins so completely that even light cannot escape. That is the clean definition, the one you put on a textbook cover to make it look brave. The messier truth is that a black hole is what happens when you cram a lot of mass into too small a volume. Nature has a limit to how politely matter can hold itself up. Atoms do not like being squeezed. Electrons occupy quantum states, and they resist being forced into the same ones. There is a kind of microscopic stubbornness built into matter. But gravity is also stubborn, and gravity is patient. Given enough mass, gravity keeps compressing until the normal supports fail. First, ordinary pressure fails. Then, electron degeneracy pressure, the thing holding up white dwarfs, fails. Then neutron degeneracy pressure, the thing holding up neutron stars, fails. And if there's enough mass left after those defenses collapse, the core continues inward, not because it wants to, but because there is no force left that says no. The result is a black hole. Not a predator, not a demon, just the final outcome of gravity doing paperwork. You might wonder what enough mass means, and I could tell you numbers, but numbers are for people who think they control things. So instead, imagine a star so heavy that its own weight becomes a trap. During its life, it burns fuel in its core, fusing light elements into heavier ones. That fusion releases energy, and the energy pushes outward. It is a constant argument. Gravity pushes in, pressure pushes out. For millions of years, sometimes billions, the star holds that balance. It glows because it is spending itself to stay upright. Then, the fuel runs out, and the outward push weakens. Gravity does what gravity always wanted to do. The core collapses. The outer layers may explode outward in a supernova, a bright tantrum. But the center can keep falling and falling and falling. And at some point, a boundary forms, a line in space-time beyond which escape is no longer a word that makes sense. That boundary is what you are drifting toward now. You do not feel it yet. At this distance, gravity is a gentle suggestion. It is like standing on a slope that is almost flat. You may even feel peaceful if your mind is willing to confuse calm with safety. Space is good at that. It offers you quiet, and it charges you with death. The dark spot grows not because it is coming at you, but because you are moving into its influence. And still, it does not look like anything special. There is no sign that you are approaching a point of no return. No cosmic warning label. No celestial tape across the doorway. Just a missing piece of sky and your own motion. And here is the dull truth that makes black holes more frightening. You are always falling in gravity. Even now, in your bed, you are falling through curved space-time toward Earth. The ground simply gets in the way and calls itself support. Out here, you have no ground, so your falling is honest. As you drift closer, you may start to notice something subtle about the starfield. The stars around the dark patch look slightly distorted. Their positions seem wrong. like a reflection in rippling water. That is gravitational lensing. Light does not travel in perfect straight lines through curved space-time. It follows the straightest path available, which can look curved to you. So, a black hole can act like a lens. It can bend light from objects behind it, wrapping the background around itself. You are watching geometry misbehave, and it does it quietly, like an office worker redirecting your email into a folder you will never check. The dark spot is still the most obvious feature, though. It is the place where the bending becomes so extreme that the light loops in or plunges inward, and you keep falling because the thing about a slope is that you do not need to be dragged. You just need to let go. And as you keep falling, it helps to know what a black hole actually is, because the name makes it sound like a creature when it's really a place. You are still outside it. You are still in a region where physics behaves, more or less, like the physics you grew up with. You have gravity, you have inertia. You have a sense of direction that includes words like away. A black hole, from far away, is a mass like any other. If you could hold position here at a respectful distance, you could measure its pull. You could chart orbits around it. You might even be disappointed. It would not look like a swirling void unless it had material around it. In empty space, a black hole is hard to find. It announces itself mostly by what it does to other things. Stars orbiting something invisible, gas heating up and glowing as it spirals inward, light bending in a way that makes the background look wrong. It is not a thing you see, it is a thing you infer, and that is part of why it feels like cosmic horror. It is the universe teaching you that reality is not obligated to be visible. The special feature of a black hole is not its darkness. Darkness is common. The special feature is its boundary. At some radius from the center, the escape velocity becomes equal to the speed of light. That is an old and simple way to say it. Escape velocity is the speed you need to leave an object's gravity without falling back. On Earth, it is high enough to be annoying and expensive. On a black hole, it becomes impossible because nothing can go faster than light. But the deeper truth is not about speed. It is about space-time itself tilting. Imagine you are walking on a moving walkway at an airport, the kind that always smells faintly like rubber and exhaustion. If the walkway moves slowly, you can walk against it. You can go back. If it moves faster, you have to work harder to make progress. You can still go back, but it is annoying. If it moves at the fastest speed you can walk, then you can stand still relative to the building, but you cannot walk backward. Your best effort only holds you in place. Now, imagine the walkway moves faster than you can possibly walk. Backward is gone. Not because you are weak, but because the environment has removed the option. That is what the event horizon is like in spirit. Space-time is flowing inward in a way that makes outward paths no longer lead outward. It is not a wall. It is not a surface you could scrape with a fingernail. It is a boundary in the structure of possible, and you are drifting toward it with the calm inevitability of a spoon sinking in thick soup. Black holes come in different sizes. Some form from collapsing stars, a few times the mass of the sun, compact and severe. Others are supermassive, millions to billions of solar masses, sitting in the centers of galaxies, like silent landlords. And size matters because the larger the black hole, the gentler the gravity feels at its horizon. This is one of those facts that sounds like it should be backwards. It feels wrong, so it must be true. A small black hole has a small event horizon. That means the change in gravity over a short distance is intense. Tidal forces, the difference in pull between your head and your feet, become strong quickly. A supermassive black hole has a much larger horizon. At that boundary, gravity can be relatively gentle. You could cross it without immediate drama, like stepping over a line drawn in faint chalk. Of course, the drama arrives later. The universe is polite like that. It lets you get comfortable before it makes its point. For now, you are still outside. You could, in principle, turn around. But turning around is not as simple as deciding to. You would need thrust. You would need fuel. You would need the kind of planning humans like to do in safe rooms, not in falling elevators. Without thrust, you follow your orbit or your plunge like a bead on a wire, and your plunge is quiet. The dark spot grows. The star field warps more. Your sense of direction becomes less trustworthy. There is no up or down in space, but gravity gives you something like down, a direction your path wants to point. And here, down is not toward a surface. It is toward an idea. The core of a black hole is not a place you can imagine easily. Your brain was built to understand trees and faces and the sound of rain on a roof. It was not built to understand a region where time behaves like a direction you cannot avoid. So you do what brains do. You use metaphors. You picture falling into darkness. You picture a tunnel. You picture a pit. And those pictures will help you emotionally, but they will mislead you physically. Because a black hole is not empty. It is not a hole like the hole in a donut. It is a region of space-time, shaped by mass and energy. And it has structure. There is the accretion disk. Sometimes, if there is material spiraling in, there are jets. Sometimes, if magnetic fields fling particles outward along the poles, there are photons skimming close to the horizon, trapped in precarious orbits, circling like moths around a porch light that hates them. And there is the horizon itself, which you are nearing. Speaking of boundaries, there's a particular edge you're approaching, an edge that doesn't feel like an edge at all. If you are expecting a visible line, you will be disappointed. There is no glowing ring that says event horizon. There is no crackling energy field. In many cases, you would cross it without noticing anything special in the moment. That sounds comforting until you understand what it means. It means the point of no return does not feel like a choice. The event horizon is defined by light. Light is the fastest messenger the universe allows. If light cannot escape from a region, then nothing can send information out from there. So, from the outside, the horizon is an information boundary. From your point of view, falling in, your local physics feels normal for a while. You still have your heartbeat. You still have thoughts, if you brought them with you. You still see stars, though their light is distorted and concentrated in strange ways. But to a distant observer, something eerie happens as you approach the horizon. They see you slow down, not because you are actually slowing in your own frame. You feel yourself falling, but your signals to the outside take longer and longer to climb out. Light leaving you gets stretched. Its wavelength lengthens. It shifts toward red, then infrared, then radio, becoming weaker and weaker. So, the outside universe sees you fade, as if time itself is getting sticky. This is gravitational time dilation. Gravity affects time. The closer you are to a massive object, the slower your time runs relative to someone far away. This is not philosophy. It is measured. Your phone's navigation relies on it. Global Positioning System satellites have to correct for the fact that time runs differently in orbit than on Earth. If they did not, you would get lost quickly in a very boring and expensive way. Near a black hole, this effect becomes extreme. From far away, you never quite cross the horizon. You just approach it, slower and slower, dimmer and dimmer, like a video buffering forever. To you, nothing like that happens. You cross infinite time. You do not freeze. This mismatch is not a trick. It is the universe being consistent from different viewpoints in a way that makes your intuition feel small. And as you approach, the horizon becomes less like a line and more like a region where out becomes harder. You could imagine trying to shout to the outside. Your voice would not travel, of course, because there is no air, but you could imagine sending a radio signal, a pulse, a message. Each message would be more tired than the last. Each would lose energy climbing away from the gravity well. It is like trying to toss coins out of a deep pit. At first, some make it. Then, only the strongest throws. Then none. The event horizon is where even your best throw cannot escape because the pit has become too deep. And here is the quietly unsettling part. You do not feel it as a barrier. If the black hole is supermassive, the horizon can be so large that the tidal forces at that boundary are small. You might feel normal, almost bored. You might cross the horizon thinking, this is it. This is the famous edge, and it feels like nothing. Congratulations. You have just entered a region of space-time that cannot inform the rest of the universe that you exist. There is no alarm, no shaking, no sudden heat, just the gentle continuation of falling. You might look back, if you can call it back. You might see the outside universe concentrated into a bright disk above you, light warped around the hole. You might see your own ship's lights reflected strangely. You might see the stars compressed into a ring, an optical effect created by extreme bending of paths. And still, the horizon is not a surface. It is a mathematical boundary. For a non-rotating black hole, the simplest kind, called a Schwarzschild black hole, the horizon is a sphere. A smooth, silent sphere in space-time. For a rotating black hole, called a Kerr black hole, things get more complicated. Rotation drags space-time with it, like stirring thick honey. The horizon changes. There is an ergosphere outside it, a region where space-time is dragged so strongly that nothing can stay still relative to distant stars. In that region, you can still escape, but you cannot hover. You must move with the flow. Black holes, in reality, are likely rotating because the stars that form them rotate, and angular momentum is another one of nature's stubborn rules. So your fall may include this dragging, this twisting of possible paths. But the overall story remains. There is an edge where escape ends, and it does not feel like an edge. But once you're past that quiet edge, the next thing that matters is time. Yours and everyone else's watching from a safe distance. Time in your daily life is the background hum you ignore. It is the clock on the wall, the date on a form, the slow decay of coffee warmth. Near a black hole, time stops being background. It becomes a character. You are falling inward, and your own time feels steady. Your heart beats. Your thoughts tick forward. You might even check a watch if you are the kind of person who brings a watch to an execution. It behaves normally for you, but outside, the universe is running on a different schedule. The further you fall, the less you agree about now. If you could see someone far away watching you, you would see their movements speed up. Their clocks would seem to race. They would age faster than you in your view. To them, you are the one slowing down. This is not because either of you is wrong. It is because time is not absolute. It is part of the geometry. In general relativity, mass and energy curve space-time, and that curvature affects the paths of objects and the flow of time. The deeper you are in a gravity well, the less time you get compared to someone higher up. On Earth, the difference is tiny, but real. Clocks at sea level tick slightly slower than clocks on mountains. Your head is aging faster than your feet by a ridiculous amount. Nature is petty like that. Near a black hole, the difference becomes dramatic. This creates a strange emotional effect, even if you are trying to stay calm. It means that falling into a black hole is not just moving through space. It is moving into a region where your connection to the rest of the universe becomes mismatched. You do not simply disappear. You become out of sync. Imagine you are trying to have a conversation with someone while walking into a tunnel. At first, you can still hear them. Then their voice echoes. Then it fades. But in a black hole, the fading is not about distance. It is about time and energy. If you tried to send a final message outward, it would climb away with difficulty. As it climbs, it loses energy. The message gets redshifted, its frequency drops. A bright signal becomes dimmer. A sharp ping becomes a low, slow wave. By the time it reaches far away, it might be so stretched that it blends into background noise. So even if the outside universe could, in principle, receive something from you just above the horizon, the message becomes less legible. It is like writing your last words in ink that gradually turns invisible as it dries. And if you are already inside the horizon, then the issue is even simpler. There are no outward paths for light. You can still shine a flashlight. The photons still leave the bulb, but their paths curve inward. They do not go out. It is not that they slow down. Light always travels at light speed locally. It is that space-time itself is arranged so that all future-directed paths point inward. This is where the metaphor of a waterfall becomes helpful. Outside the horizon, you can still swim upstream with enough effort. At the horizon, the current reaches light speed. Inside, the current exceeds any swimming ability. So time itself becomes like a downstream direction you cannot fight. Your future is toward the center, in the same way your future is toward tomorrow. You can't decide not to have tomorrow, at least not by willpower alone. You can only decide what you do on the way. And this gives the event horizon its quiet cruelty. It is not a trap you feel. It is a trap in the map of possible futures. From the outside, you look frozen at the edge. From the inside, you keep going. Both views are true, and they never get to reconcile because the horizon prevents the reconciliation. Even if you could scream, even if you could broadcast, even if you had the best antenna in the galaxy, the universe has arranged it so your story does not propagate outward. It is not personal. It is geometry. Time is already bending, but the real physical danger comes from how gravity changes across your body. Quiet at first, then not. Gravity does not pull evenly. It pulls harder on what is closer. On Earth, you live with this and barely notice. Your feet are slightly closer to the center of the planet than your head, so gravity is slightly stronger at your feet. This difference is tiny. Your body does not get stretched into a noodle. You are allowed to keep your shape. But near a black hole, the difference can become catastrophic. This difference in gravitational pull across an object is called tidal force. It is named after ocean tides, which are caused by the moon's gravity pulling more on the near side of Earth than the far side. The moon gently kneads the oceans, and the oceans respond by sloshing. A black hole does not gently knead. It does not have that kind of patience. As you fall, the part of you closer to the black hole feels a stronger pull than the part farther away. So you begin to stretch along the direction of fall. At the same time, you get squeezed sideways. This is because gravity is pulling everything toward the center, so your sides are being pulled inward. Stretch lengthwise, squeeze sideways. This is the beginning of spaghettification. It sounds silly, which is convenient, because your brain prefers silly words for terrifying processes. Spaghettification is what happens when tidal forces pull your feet faster than your head, until you are elongated. If the black hole is small, this can start outside the horizon. You could be torn apart before you ever cross the famous edge. If the black hole is supermassive, the horizon is so large that the tidal forces there can be mild. You might cross the horizon intact, still annoyingly whole, but the tidal forces keep increasing as you fall inward. Eventually, they win. So the size of the black hole changes the order of events, but not the ending. Let's make it personal. Since you are the one falling, you are oriented feet first, because most nightmares prefer tradition. Your feet are closer to the center. They accelerate slightly more than your head. At first, the difference is subtle. It is like someone gently tugging at your ankles. If you were in a ship, your body might just feel a small strain, a stretching sensation. But as you go deeper, that tug becomes a pull. Then it becomes a demand. Your bones are strong, but they are not designed for this. Your muscles are elastic, but not like that. Your blood, your organs, your nerves, all of it is held together by molecular bonds that expect a certain range of forces. Gravity near a black hole does not care what your tissues expect. Tidal forces increase, roughly, with the inverse cube of distance. That means if you get twice as close, the stretching gets about 8 times worse. It escalates quickly, like a minor problem you ignored until it grew teeth. At some point, your body can no longer act like a single object. Different parts want to follow different paths. Your feet are being told by space-time to go inward faster than your head. Your head is being told to lag. The connection between them becomes the problem. First, you might feel an uncomfortable stretching if you are still alive and still capable of feeling. Then you would feel pain because your nerves would protest. Then, if the forces continue to rise, you would lose integrity. Congratulations, you are now a set of components, each following its own geodesic, its own straightest path through curved space-time. There is a grim comfort here. The good news is that the process becomes too fast for prolonged suffering, especially near small black holes. The bad news is that this is because your nervous system stops being a system. For a supermassive black hole, the tidal forces at the horizon might not kill you immediately. You could, in theory, have time inside, time to think, time to be aware of your isolation. That is arguably worse. If you were falling into the supermassive black hole at the center of a galaxy, the horizon could be so wide that you would cross it without noticing. Then you would continue falling, still intact, while the tidal forces slowly increase. It would feel like a steady stretching, growing stronger as you go. And because your own time is normal, you might have minutes, maybe hours, depending on the mass and your trajectory, before the forces become lethal. It is enough time for dread to settle in. Enough time to realize that this is not a dramatic instant. It is a gradual loss of options. And while your body is dealing with that uneven pull, the space around you is doing something else, warming up in a way that looks beautiful from afar. Not every black hole is surrounded by fireworks. Some are quiet, starving, drifting through space with nothing nearby to eat. Those are the gentlest, in a way. They offer you the dignity of darkness. But many black holes live in messy neighborhoods. They sit in regions with gas, dust, stars, shedding material, or unlucky companions in binary systems. And when matter falls toward a black hole, it does not usually drop straight in. It spirals. This is because matter has angular momentum. It is already moving sideways as it approaches. So, instead of a clean plunge, it forms a disk, a flattened, swirling structure called an accretion disk. Accretion is a soft word for a violent process. It means growth by gathering, but the gathering is not gentle. The disk is crowded. Different layers of gas rub against each other. Friction and turbulence convert orbital energy into heat, and heat in space is not cozy. Heat is radiation. Heat is X-rays. Heat is ultraviolet light that tears molecules apart. So, the region around a feeding black hole can be the brightest thing in a galaxy. The hole itself is dark, but the traffic jam around it glows like a welding torch. From far away, you might see a luminous ring, a bright disk with a dark center. Closer in, you would see the disk as a storm of plasma, magnetized gas, spiraling at a significant fraction of light speed. It would not sound like anything because, again, no air, but visually, it would be harsh and energetic. If you drifted into that region, the radiation could cook you before gravity ever gets the chance. This is the second insult. The black hole might not kill you first. Its environment might. The accretion disk can be hotter than the surface of many stars. It can emit radiation that strips electrons from atoms, turning matter into plasma. And plasma is not a substance you want to be near without very serious shielding. Plasma is matter with its manners removed. So if you are approaching a black hole that is actively feeding, your journey is not a quiet fall through ink. It is a fall toward a bright, violent ring of death. You might see arcs of light, hot spots, flares where magnetic fields reconnect and dump energy. You might see matter in the disk moving so fast that relativistic effects change its brightness. The side of the disk moving toward you appears brighter because of relativistic beaming. The light is concentrated in the direction of motion. The side moving away appears dimmer, so the disk is asymmetric. One side looks like it is shouting, the other side whispers. And if the black hole is rotating, the inner edge of the disk can be closer in, because rotation allows stable orbits at smaller radii. Close to the horizon, matter can circle a few times before plunging. Those last orbits are the last moments of material still outside, still in the universe, that can communicate outward. Then it crosses, and the light it would have emitted no longer escapes. This is how black holes stay dark, not because they are empty, but because the light produced inside cannot come out. If you are very unlucky, you might also see jets. Some black holes launch narrow beams of particles along their rotation axis. These jets can extend for enormous distances, blasting energy into interstellar space. They are thought to be powered by magnetic fields, twisted by the rotating disk and the rotating black hole. It is like the black hole is a generator converting rotation into electromagnetic violence. If you drift into a jet, you do not get a scenic tour. You get your atoms rearranged. But perhaps tonight, for the sake of sleep, you are not that unlucky. Perhaps you are falling into a quieter black hole. A black hole with little food nearby, no bright disk, no screaming radiation, just darkness. In that case, the approach feels almost serene. The star field still warps, the dark patch still dominates, and your danger is not heat, at least not yet. It is the steady rise of tidal forces, the growing disagreement between different parts of your body about how fast to fall. And whether the neighborhood is bright or calm, the direction of your journey stays the same. Downward, toward the center where the simple rules stop being simple. Inside the horizon, downward is not a metaphor. It is the direction of your future. You cannot turn around not because you lack courage, but because the structure of space-time gives you no path that leads outward. It is like being inside a maze where every corridor leads deeper and the exit is painted on the wall. Still, physics continues to operate locally. Your atoms still obey electromagnetic forces. Your chemistry still exists for as long as you remain intact. You are not instantly erased. You might wonder, in a quiet corner of your mind, what you are falling toward. People talk about the singularity, the center, the point of infinite density. It is an unsettling phrase, singularity. It suggests a point where normal rules collapse. And that is, in a sense, what it is. But it is also a sign that our understanding is incomplete. A singularity in math often means the math has been pushed beyond its domain. General relativity predicts that inside the black hole, matter collapses toward a point, and the curvature of space-time becomes infinite. Infinite is not a number you can visit. Infinite is the word you use when your equations stop being polite. It is the universe's way of saying, you have taken this model as far as it goes. It works beautifully outside. It predicts orbits, lensing, time dilation, but at the center, the theory yields a result that likely indicates missing physics. Quantum mechanics, the rules governing the small, does not fit neatly with general relativity, the rules governing the large. Inside the black hole, you have both. Enormous mass in tiny volume. So the center is where the story breaks. You can think of it like reading a book where the last pages have been torn out. You can infer what might happen, but you cannot claim certainty. And the black hole will not tell you. It does not send updates. For now, you continue falling. If the black hole is non-rotating and uncharged in the idealized textbook sense, your path to the singularity is straightforward. Your remaining time, once inside, is finite. This is another quiet cruelty. From your point of view, you do not fall forever. You reach the center in a limited amount of your own time. For a stellar mass black hole, that time might be a fraction of a second from horizon to center, barely enough to register a thought. For a supermassive black hole, it could be longer, minutes, maybe more, long enough for your mind to wander if your body is still together. But as you fall, the tidal forces ramp up. The stretching becomes severe. Even if you cross the horizon intact, deeper in, you will not remain intact. Your body becomes a lesson in differential gravity. First, you elongate, then you thin. Then your molecules are pulled apart. Chemical bonds are electromagnetic in nature. They are strong on human scales, but gravity near the center is not human scale. Eventually, even atomic nuclei can be disrupted, and the pieces of you continue inward, each following its own path. You might find it comforting, in a strange way, that the black hole does not preserve you as a suffering whole. It breaks you into simpler things. There is less you to worry, but the question remains, the one that keeps scientists awake and keeps philosophers employed. If you fall in, what happens to the information that described you? Not your feelings, not your regrets, the actual physical information, the arrangement of particles, the quantum state. In physics, information is not supposed to be destroyed. At least, that is what our best theories suggest. So black holes become a problem. They appear to swallow information and hide it behind the horizon. If the black hole later evaporates, as some theories say it does the information come back, or is it lost? This is called the black hole information paradox. A paradox is just a polite word for we are confused, and confusion is honest. Physicists have argued about this for decades. Some suggest that information is somehow encoded on the horizon itself, like a hologram. The idea is that the boundary holds the record, even if the interior is inaccessible. Others explore ways the information might leak out in subtle correlations in the radiation emitted by the black hole over time. The details are complex, and the arguments can become sharp. But the sleep-friendly summary is this: the universe seems to dislike losing track of things. It will tolerate your death. It will tolerate your disassembly, but it may not tolerate your complete erasure from its bookkeeping. That is oddly comforting if you are the kind of person who wants to be remembered by thermodynamics. But We are not at the evaporation yet. We are still falling. And while your personal story inside the horizon ends quickly, from the outside, the black hole can sit there for a very long time. It can orbit in the galaxy. It can merge with other black holes, sending gravitational waves rippling through space-time. Those waves are real, measured by detectors on Earth that can sense changes smaller than an atom's width. Two black holes collide, and space-time rings like a bell. Even that is quiet in its way, a vibration through nothing. But that is a different story. Tonight, your story is the slow approach, the gentle crossing, the mismatch of clocks, and the eventual stretching. And now, you are deep enough that the environment, if there was an accretion disk outside, is no longer visible as a normal sky. Light from outside is distorted. Your view of the universe compresses into strange shapes. The horizon behind you does not look like a wall, but it behaves like one for signals. Your ability to affect the outside is gone, and you are left with what you can still experience, which is mostly the steady increase in forces trying to pull you into a line. Your body, if it were still cohesive, would now be under stress that no biology evolved to handle. Evolution prepares you for predators, infections, and awkward conversations. It does not prepare you for space-time gradients. In a sense, this is the most honest thing about black holes. They are not tailored to you. They do not have cruelty. They have indifference. And indifference is efficient. You might think of the black hole as an ending, but it is also a kind of archive. It takes in mass, energy, and angular momentum. From the outside, those are the only things you can reliably say it has. This is the no-hair idea. Black holes are simple in a way that feels insulting. They do not keep the details visible. They reduce complexity to a few numbers. Your entire life, your entire structure, your entire history becomes, from the outside perspective, just a little more mass and a little more spin. Congratulations, you have been compressed into accounting. But that simplicity is part of why black holes are useful to physics. They are clean problems. In a universe full of mess, they let us test gravity in extreme conditions. They let us ask questions about the nature of space and time. They let us confront the edges of our theories, where the math starts to cough. And, in the meantime, they remain what they were when you first saw that missing patch of stars, a place where back stops meaning anything. You may notice, as you keep falling, that the idea of lasting a day inside a black hole is almost humorous. A day is a unit of time based on Earth's rotation. It is the planet turning like a sleepy animal under sunlight. Inside a black hole, the universe does not care about your calendar. Your proper time to the center depends on the black hole's mass and your path. For many black holes, you do not get anything like a day. You get seconds or less. Even in the supermassive case, where you might have more time, the tidal forces will eventually tear you apart. So the phrase, "you wouldn't last a day," is not a challenge. It is an understatement wearing a lab coat. Still, the journey there, the approach, the horizon, the time dilation, these are the parts you can hold gently in your mind. They are the slow, quiet mechanisms. They are the boring machinery of doom. And boredom, in the right tone, is perfect for sleep, because the black hole is not a jump scare. It is an inevitability you can narrate like rainfall. And with that, you drift deeper into the idea of the center, the place our equations call a singularity, the point where our current story runs out of pages and where the universe, as always, refuses to explain itself in simple words. So you keep reading with your fingertips, feeling for the next paragraph and finding only smooth paper where words should be. You are still moving, though. That is the part nobody tells you in the glossy pictures. Even when the story ends, the motion does not. Inside the horizon, you do not get to hover and contemplate. Hovering is an outside luxury. In here, every possible tomorrow points inward. You can call it falling, if that comforts you, but it is stranger than that. It is more like time has been rotated just a few degrees until the center becomes not a place you visit, but a moment you must reach. That is why the singularity is such an annoyance to physicists. It is not just a dot on a diagram. It is the point where the theory says, inevitably, all world lines go. A world line is your path through space-time. It is the trail of your existence, drawn in 4 dimensions. Outside the hole, you can pin that trail with engines or muscle or careful orbital choices. Inside, your trail is railroaded. Now, if this were a simple non-rotating black hole, the kind built for textbooks and polite lectures, you would be done fairly quickly. From horizon to center, you get a finite slice of your own time. The unsettling part is how ordinary that slice feels at first. You do not feel infinity. You do not feel cosmic significance. You feel pressure changing across your body. You feel orientation become less meaningful. You feel the growing insistence of tidal forces, like a hand that keeps tightening. And somewhere between one heartbeat and the next, your molecules stop agreeing that they belong together. But the singularity is not the only problem hiding in the center. It is just the most dramatic one. Because the truth is, we do not have a completed theory for what happens when gravity becomes that intense at that small a scale. General relativity is brilliant at describing the curve of space-time. Quantum mechanics is brilliant at describing the jittery, discrete behavior of matter and fields. Put them together in a black hole's interior, and you get an argument that never ends. 2 very confident frameworks, both correct in their home neighborhoods, staring at each other across a boundary and refusing to share vocabulary. So when you hear the word singularity, what you should picture is not a physical object. You should picture a warning light on the dashboard, the kind you ignore for a week because the car still runs, until it does not. The equations are still running. They just stopped telling a sensible story. And that is why black holes became more than astrophysics. They became philosophy with good math. Because when the universe refuses to explain itself, your species fills the silence with questions. The most persistent question is not, what happens to you? You are chemistry, briefly coherent, and then you are not. The persistent question is, what happens to the information that described you? Information is a cold word for a warm thing. It means every detail that makes you you, at least physically. Every particle state, every correlation, every quantum relationship. Physics, at least the physics people like, does not enjoy losing information. In ordinary quantum mechanics, evolution is unitary. That means the math keeps track. It lets you run the film forward and backward, at least in principle, without losing the plot. A black hole seems to break that promise. From far away, a black hole looks like a simple object. Mass, spin, and maybe electric charge, though charge tends to neutralize fast in an astrophysical mess. Everything else, the details, the so-called hair, is hidden. So you get a problem that is almost insulting. You can throw in a library, a wedding ring, a hard drive full of cat pictures, an entire star. From the outside, the whole just gains mass. It does not advertise what it ate. And then, years later, you remember another unpleasant detail. Black holes do not just sit there forever in perfect silence. They leak, not like a dripping pipe, not like air escaping a balloon. They leak in a way that feels like the universe cheating at its own rules. This leak is called Hawking radiation. It is named after Stephen Hawking, who took a black hole, a horizon, and quantum field theory and asked what happens to the vacuum near that boundary. The answer is quiet, technical, and deeply rude. You like to imagine vacuum as nothing, a clean absence, a blank page. Wrong. Vacuum in quantum field theory is restless. Fields still exist. They fluctuate, they jitter. They briefly borrow energy in a way that is allowed by the uncertainty principle, then pay it back quickly. A common story says particle pairs pop into existence, and one falls in while the other escapes. It is a decent mental picture, like a bedtime fable with sharp edges. The more precise view is that the horizon changes what different observers call a particle. What looks like empty vacuum to you far away does not look the same to an observer accelerating or hovering near the horizon. The horizon divides space-time into regions, and quantum fields do not like being divided without consequences. The consequence is that, to a distant observer, the black hole emits radiation with a thermal spectrum. Thermal means it looks like heat. A black hole has a temperature, and because it emits energy, it loses mass very slowly for a large black hole. But it loses mass, which means, given enough time, it evaporates. And now, the information problem becomes sharper. If the hole evaporates away into featureless thermal radiation, where did the information go? Did the universe actually delete a book from its own accounting system? Or did the information get encoded in the radiation in some subtle way? If it is truly thermal, truly random, then the original details are gone. That would mean a fundamental breakdown. It would mean quantum mechanics, or at least the comfortable version of it, is incomplete. And physicists tend to react poorly when their favorite conservation laws get threatened. So they argued. For decades, the argument ran like a slow war fought with preprints. Some people said information is lost. Some said it is preserved. Some said the question itself is misguided. And while they argued, you kept falling in your imaginary plunge toward an interior we cannot fully describe. But you do not have to reach the singularity to feel the paradox. It starts at the horizon, because the horizon is an information boundary, not just for your flashlight beams, for the deep bookkeeping of the universe. There is a concept you should hold gently here, because it is both simple and weird. Entropy. Entropy is often described as disorder, that is, the lazy translation. The better translation is the number of microscopic ways to arrange a system while keeping the same macroscopic appearance. A shuffled deck has higher entropy than a perfectly ordered one because there are more ways to be messy than to be arranged. Entropy is also tied to information. If you have high entropy, you need more information to specify the exact microstate. Now, black holes have entropy. This is not poetry. This is physics that ended up on chalkboards, then in textbooks, then in Nobel speeches. Jacob Bekenstein in the 1970s suggested that a black hole must have entropy proportional to the area of its horizon, not its volume. Its area. That is a strange clue. Because it suggests the information content of a black hole scales with its surface, like a storage device where only the skin matters. Stephen Hawking's calculations supported the thermal radiation idea, and the entropy formula became concrete. Black hole entropy is huge, enormous. A black hole can hold an absurd amount of information, in the sense of entropy, compared to ordinary matter. And yet, from the outside, it looks bald, simple. A minimalist object with a violent reputation. So where is the information stored? If it is stored at the horizon, then the horizon is not just a geometric boundary. It is a kind of ledger. This is where the holographic idea enters, wearing a cloak of math. The holographic principle suggests that in certain situations, the physics inside a volume can be described by information encoded on the boundary of that volume, like a hologram on a credit card, where a flat surface encodes a three-dimensional image. In black hole terms, it implies what falls in might be encoded on the horizon in some scrambled way. Not as a photograph, not as a readable list, more like a smear of quantum correlations, spread thin but preserved. If that is true, then when the black hole radiates away, the information could leak out in the outgoing radiation, not as obvious messages, but as subtle patterns. The radiation would not be perfectly random. It would be correlated in a way that carries the imprint of what fell in. That sounds comforting until you remember what it means for you personally. It means you might not be erased. You might be archived, compressed, encrypted by the universe with a key nobody owns. Congratulations. You have become an unreadable backup file. Now, if you are lying in bed listening to this, you may wonder why anyone cares. You are not planning to fall into a black hole tomorrow. You are mostly planning to survive until morning and maybe find water. People care because the information problem is not just about black holes. It is about whether the universe is consistent with itself. If a black hole can delete information, then the laws you trust in ordinary quantum experiments are not universal. And that is not an academic worry. It means the universe has exceptions, and exceptions are where reality hides its knives. So, physicists tried to resolve it. Some propose that information escapes in Hawking radiation. Others propose that information remains inside, and the black hole leaves behind a remnant, a tiny object that stores everything and refuses to go away. A remnant is convenient, but it introduces other problems. If remnants can store arbitrarily large information, you have to explain why the universe allows such things and why they do not flood the cosmos. Others proposed more radical ideas, that the interior is not what you think, that horizons have structure, that perhaps, in some sense, the interior is encoded elsewhere. And then there is the idea that tries to keep everyone unhappy. Complementarity, black hole complementarity, suggests that no single observer sees a violation. To the outside observer, information never truly crosses the horizon. It gets thermalized and stored at the horizon, then re-emitted. To the infalling observer, you cross the horizon smoothly, and nothing special happens there. Both stories are valid, but no one can compare notes because the horizon prevents it. It is a diplomatic solution built on causal separation, a treaty signed in a room where the negotiators can never meet. And then, as always, someone found a way to make it worse. Because if you insist that information is preserved and carried out in Hawking radiation, and you also insist that an infalling observer sees nothing special at the horizon, you can end up with contradictions involving quantum entanglement. This led to the firewall argument, a suggestion that, to preserve unitarity, the horizon might not be smooth. Instead, it might be a region of high-energy quanta, a kind of burning barrier that destroys infalling observers. A firewall. A lovely name, really. It makes the event horizon sound like a corporate security feature. If firewalls exist, then your calm crossing of the horizon was a lie. You would hit a wall of violent quantum effects and be shredded right at the boundary. That would solve some paradoxes by sacrificing your comfort. The universe is good at solving problems by eliminating the person asking them. But it is not settled. Most working physicists do not treat firewalls as confirmed reality. They treat them as a sign that our understanding of quantum gravity is still under construction. So for now, in your quiet fall, you can keep the original mood. Smooth horizon, delayed doom, and an interior that remains hidden. The important part is that black holes are not just astrophysical drains. They are tests. They take your best theories and squeeze them until the seams show. And if you want a dark, sleepy thought, here it is. The seams are showing because the universe is not obligated to be comprehensible at your scale. You are a primate with a nervous system optimized for fruit and social hierarchies. You are trying to parse the behavior of space-time under extreme curvature. Of course, it feels like the last page is missing. Now, you might ask, if the interior is unknowable, why do we trust anything we say about it? Why do we talk about horizons and singularities as if we have been there? Because the exterior math is reliable. General relativity has been tested in gentler regimes with precision. We see gravitational time dilation. We see light bending. We see gravitational waves from black hole mergers. We see stars orbiting invisible masses in galactic centers. We see accretion disks glowing and spectra shifting. So we infer. And we build models. And the models are remarkably good at predicting what we observe from a distance. But the interior remains a region where observation cannot reach. Not with light, not with signals, only with theory. And theory is a kind of dreaming with equations. You might imagine in your fall that the interior is a chamber you can explore, but exploration requires return, or at least reporting. Inside the horizon, reporting is gone, so your role shifts. You are no longer an explorer. You are a thought experiment, a sacrificial character in a story told to test consistency. You might not find that flattering. It is not meant to be. Now, to keep things grounded, let us step back outward for a moment. Not physically, you cannot do that, but conceptually, we can return to the horizon and look at it from the safer side. Because outside observers have their own strange experience of black holes, they never see you cross. They see you fade, redshift, and slow. So, in a sense, for the outside universe, the horizon behaves like a surface that collects things. Matter falls in, and from the outside view, it seems to pile up near the horizon, dimming and stretching, never quite disappearing. In practice, the light becomes so red-shifted and faint that it effectively vanishes. But the mathematical description has this asymptotic approach. This leads to a quiet, almost bureaucratic picture. The horizon is like an inbox. Things arrive. They get processed. Their details are not visible, but their mass and angular momentum change the black hole's parameters. If the black hole is rotating, the horizon area can grow in specific ways. And there is a kind of thermodynamics here. Black hole mechanics mirrors the laws of thermodynamics. There is a first law relating changes in mass to changes in area and spin and charge. There is a second law stating that the horizon area never decreases, at least classically. Area increases like entropy increases. The third law has its own flavor about not reaching absolute zero surface gravity in finite steps. This was one of the great jokes the universe played on theorists. An object that seemed like pure gravity, pure geometry, ended up behaving like it had temperature and entropy. It is almost as if space-time itself has microscopic degrees of freedom, almost as if the smooth curve is an average of something deeper. But we do not have full access to that deeper description yet. So again, you reach the missing pages. Now, while all of this plays out in the abstract, black holes do something very concrete in the universe. They merge. Two black holes orbit each other, losing energy through gravitational radiation. Their orbit shrinks. They spiral inward. At the end, they collide and become one. This is not like two rocks hitting. There is no surface contact. It is the merging of space-time geometries. During the final moments, the system emits gravitational waves, ripples in space-time that propagate outward at light speed. Those waves stretch and squeeze distances as they pass. Not by much by the time they reach Earth, but enough that detectors can notice. Laser interferometers with arms kilometers long can measure changes smaller than a proton's width. They do this by comparing the phase of laser light traveling back and forth. It is a delicate measurement in a noisy world. When a gravitational wave passes, it changes the effective length of the arms differently. The interference pattern shifts. And from that shift, scientists can infer the masses and spins of black holes billions of light years away. This is one of those moments where human ingenuity feels impressive. Not noble, just impressive. You are an animal that evolved to fear leopards, and you built an instrument that senses the ringing of space-time itself. Of course, you still forget your passwords. When two black holes merge, the final black hole is not immediately calm. It rings. It settles. This is called ring down. The geometry oscillates like a struck bell, emitting gravitational waves with characteristic frequencies. Those frequencies depend on the mass and spin of the final hole. This allows tests of general relativity. If the observed ring down matches the predicted modes, the theory survives another night. So far, it has survived, which is why we trust it enough to talk about horizons with confidence, even if the singularity remains mysterious. Now, let us return to the paradox again, because it is the soft haunting that hangs over this whole topic. If information is preserved, how does it get out? If it gets out, what does that mean for the smoothness of the horizon? If the horizon is smooth, how do we avoid duplication of information, which quantum mechanics forbids? In a subtle way. There is a principle called the no cloning theorem. It says you cannot make an exact copy of an arbitrary unknown quantum state. If information about you is encoded on the horizon and also you pass through, do we have two copies, an outside record and an inside original? Complementarity says no observer sees both, so no operational contradiction. But entanglement arguments complicate this. The outgoing Hawking radiation becomes entangled with the interior modes. Later radiation must also be entangled with earlier radiation if information is to come out. But quantum entanglement has constraints. A system cannot be maximally entangled with two independent systems at once. This is monogamy of entanglement, a phrase that sounds like a lifestyle choice, but is actually a mathematical restriction. So the black hole becomes a stage where fundamental principles pull against each other. Smooth horizon suggests one thing. Unitarity suggests another. Entanglement constraints suggest a third. And the resolution likely requires a full theory of quantum gravity, or at least a clearer understanding of how space-time emerges from quantum information. You can hold that thought lightly. You do not need to solve it tonight. Nobody has, but you can appreciate the shape of the problem. A black hole is where gravity, quantum mechanics, and thermodynamics all collide. And you are a little warm creature trying to think about it without raising your heart rate. Now, since your title promised a practical message, why you would not last a day, it is worth returning to your personal timeline. Assume you fell into a supermassive black hole, one of the quiet giants at the center of a galaxy. You cross the horizon without noticing. You are inside, still intact, still thinking. How much time do you have? It depends on the mass of the black hole. Larger mass means larger radius and a longer fall time from horizon to singularity, as measured by your own clock. For a hole with millions of solar masses, you might have a time on the order of seconds to minutes. For billions of solar masses, you could have longer, perhaps hours. But do not get attached to the word hours, because hours in that environment are not cozy. They are hours with tidal forces steadily increasing. In your frame, you are in free fall, so you feel weightless locally. You do not feel gravity as a force in the same way you feel standing on Earth. You feel gravity through its differences, the tidal gradients. At first, those differences are mild. Later, they become impossible. There will come a moment when your body is stretched enough that blood flow fails, tissues tear, nerves misfire, and consciousness, if it persists at all, becomes a brief spark in a storm of stress. So you do not last a day, not because the black hole is impatient, but because your coherence is not built for that gradient. And if the black hole were smaller, you would not even get the narrative luxury of minutes. The tidal forces near a small horizon can be strong enough to kill you before you cross. In that case, the event horizon is not even your problem. Your problem is that the universe is stretching you into a filament long before you get to the famous boundary. Your body becomes an instrument showing the derivative of gravity. Now, something else worth noticing, because it is often misunderstood, is the role of rotation. Most real black holes rotate. A rotating black hole has a more complex causal structure. There is an outer horizon, the event horizon, and an inner horizon, sometimes called the Cauchy horizon in the ideal Kerr solution. Between these, the geometry does odd things. In the pure math solution, there are regions that resemble tunnels and even other universes. It is the part of the story that tempts science fiction writers because it sounds like permission, but reality is not obligated to honor the clean math. The interior of a rotating black hole is likely unstable. Small perturbations, infalling matter, and radiation can pile up at the inner horizon, leading to a phenomenon called mass inflation. The name is almost comical. It sounds like a financial problem. In this context, it means the effective energy density seen by infalling observers near the inner horizon can grow without bound due to blue shift of incoming radiation. Blue shift is the opposite of red shift. Light gets compressed to shorter wavelengths, higher energy. So while signals from you to the outside get red shifted and weakened, signals falling inward can get blue shifted and intensified. Inside, there can be regions where the energy becomes enormous, not because something new was created, but because the geometry focuses and amplifies what was already there. This suggests the internal structure of real rotating black holes may be very different from the elegant Kerr diagram. So, again, the safe statement is that the interior is not well understood. What we do understand is the exterior, the horizon properties, and the emitted radiation in principle. And speaking of radiation, let us return to Hawking radiation for a moment, because it is both gentle and brutal, depending on scale. A black hole's temperature is inversely proportional to its mass. That means small black holes are hotter. A stellar mass black hole is very cold, colder than the cosmic microwave background, the leftover glow from the early universe. So it absorbs more from the environment than it emits, unless the universe gets extremely empty and cold in the far future. A supermassive black hole is even colder, so Hawking evaporation for large holes is absurdly slow. If you want a sensation instead of numbers, imagine waiting for a mountain to evaporate like morning dew. Not melt, not erode. Evaporate molecule by molecule into the air in a windless room. That is the pace. So, In the current universe, black holes mostly grow by eating gas and merging. Evaporation becomes relevant in the far future. When stars have died and the universe has cooled, that future is so distant that it makes human history look like a rounding error. But it matters conceptually, because the paradox is about that eventual fate. If the black hole truly evaporates away, it cannot keep secrets forever unless it leaves a remnant or unless information is genuinely lost. So you can see why this became an obsession. A black hole is the perfect locked room mystery, except a locked room is space-time itself. Now, since you are not actually inside a black hole tonight, we can do something your physics allows. We can step outside again and observe black holes as the universe presents them to telescopes. And what you discover, once you stop expecting them to be visible holes, is that black holes are often revealed by their companions. Consider an ordinary star orbiting an invisible partner. The star wobbles. Its spectral lines shift back and forth as it moves toward and away from you. From that motion, you can infer the mass of the unseen object. If that mass is too large to be a neutron star, and if there is no light from a normal star, you suspect a black hole. This is how many stellar mass black holes were first found. In X-ray binaries, gas from the visible star gets pulled toward the black hole, forming an accretion disk. The inner disk heats up and emits X-rays. You do not see the hole. You see the gas screaming around it. Another method is watching the orbits of stars near galactic centers. In the Milky Way, astronomers have tracked stars orbiting a central invisible mass called Sagittarius A star. Those stars move fast on tight orbits. Their trajectories imply a mass of millions of suns packed into a small volume. The simplest explanation is a supermassive black hole. And recently, you have another type of view, the Event Horizon Telescope. A network of radio telescopes across Earth used very long baseline interferometry to synthesize an Earth-sized dish. It imaged the shadow of a black hole in the galaxy Messier 87. And later, it imaged Sagittarius A star as well. What you see is not the black hole itself. You see a bright ring from hot plasma and a dark central region, the shadow, where light paths are captured. It looks like an eye, an indifferent eye. But again, it is not watching you. It is just geometry collecting photons. Those images are comforting in a strange way. They turn an abstract concept into a visible shape, but they also remind you that the horizon is not a myth. It is a real boundary with observable consequences. Now, let us pivot back inward to the information question, because it is the gentle haunting that will carry the rest of this story. Suppose you fall in. From the outside, the black hole settles. It becomes quiet again. Aside from slow accretion and the occasional merger, your details are not accessible. But does the universe keep your record? One proposal that gained traction is that information is stored in subtle degrees of freedom on the horizon, sometimes discussed in terms of soft hair. Not hair like a mane, just low-energy excitations associated with symmetries of space-time, like supertranslations. The idea is technical, but the bedtime translation is simple. The horizon may not be perfectly featureless. It may have an enormous number of ways to be slightly different, corresponding to different microstates that all look like the same macroscopic black hole. That would reconcile the entropy, and it would provide a place for information to hide. Another way to think of it is that a black hole, from the outside, is like a scrambled egg. The egg still contains the same atoms as before. The information is not lost in a strict sense, but it is dispersed into correlations that are functionally impossible to reconstruct. In ordinary thermodynamics, that is what entropy increase feels like. Not destruction of information, but practical irreversibility. The question is whether black holes are merely practically irreversible or fundamentally so. Hawking originally argued for fundamental loss, which would make the evolution non-unitary. Later, the consensus shifted toward preservation, especially with insights from string theory and holography. In certain theoretical frameworks, like the anti-de Sitter and conformal field theory correspondence, black hole evaporation appears unitary. The boundary theory does not lose information, which suggests the bulk, the black hole spacetime, should not lose it either. But translating those insights to our universe, which is not anti-de Sitter in the simplest way, is not straightforward. So you get a situation where the best hints suggest information is preserved, but the exact mechanism remains debated. That is where you are left tonight, not with an answer, but with a map of uncertainty. Now, there is a quieter, almost domestic way to appreciate this paradox. Think about burning a piece of paper. At the start, the paper has words. At the end, you have ash, smoke, heat. If you are extremely ambitious and you capture every photon of heat, every molecule of smoke, every bit of emitted radiation, and you track their quantum state perfectly, then in principle, you could reconstruct the original. In practice, you cannot. The information is dispersed into the environment. A black hole may be like that, except the dispersal is hidden behind a horizon for most of its life. Then, over very long time, it leaks away through Hawking radiation. The radiation looks thermal, like the heat from your burning paper. But if the process is unitary, the outgoing radiation must carry correlations. So the information is in the subtle patterns, not in the average glow. That means, in principle, your story could come back out, but only as an almost impossible to decode whisper in a sea of randomness. If you find that poetic, you are allowed. The universe will not reward you, but it will allow you. Now, there is another related concept that often gets mentioned in the same breath, and it is worth handling carefully: the page time. This is the approximate time when a black hole has radiated away about half its entropy, and the outgoing radiation begins to contain more accessible information about what fell in. In a certain statistical sense, before the page time, the radiation is mostly entangled with the black hole interior. After, it must start being entangled with earlier radiation to maintain unitarity. This is where the entanglement arguments get sharp. But for large black holes, the page time is enormous. So it is not relevant for your personal fall. It is relevant for the universe's bookkeeping over absurd time. So you, the infaller, do not get closure. The outside universe, if it waits long enough, might. And that is a strange asymmetry. You are the one who went in, but you are not the one who gets the ending. That is consistent with the general vibe of physics. The universe is not designed for narrative satisfaction. Now, let us shift gently to another angle, one that makes the whole thing feel more real. You might think a black hole is an isolated object, but in the universe, black holes live in environments They have accretion flows. They have magnetic fields interacting with plasma. They have companions. They have entire galaxies around them. And these environments can produce some of the most energetic phenomena known. Quasars, for example. Quasars are active galactic nuclei powered by supermassive black holes accreting matter. They can outshine their entire host galaxy, not because the black hole is shining, but because the infalling matter converts gravitational potential energy into radiation with high efficiency. A spinning black hole with a disk can extract energy from the rotation too, via processes like the Blanford and Zen-Najek mechanism, where magnetic fields tap into rotational energy and launch jets. These jets can regulate star formation in the galaxy by heating and expelling gas. So black holes are not just cosmic garbage disposals. They are engines that shape galaxies. From your bed, that might feel like overkill information, but it matters for the mood, because the universe does not place black holes as isolated traps. It weaves them into the ecology of cosmic structure. The whole is a quiet center, but the neighborhood can be loud. Now, in your falling story, you chose a quiet black hole. One without a bright disk. That made the approach calm. But calm does not mean safe. It just means the danger is less photogenic. The danger is in geometry, and geometry does not need light. So you continue inward, past the point where any outside observer can see you meaningfully. Your future narrows. Your body stretches. Your last intact thoughts, if you have them, are slow, heavy, and ordinary. And right at the edge of our knowledge, the story breaks. Not because you stop existing, but because our model stops being trustworthy. That is the honest place to leave the singularity. Not with fantasies about tunnels, but with a firm admission that the interior is beyond current tested theory. Which brings you back to the softer question you were promised. If information cannot get out, what happens to everything you were? You already know the first answer. From the outside, you become mass and spin. Your complexity is hidden. From the inside, you become torn apart and driven toward a region we cannot describe. But in the deeper accounting, the universe may still keep your trace. It may keep it on the horizon, or in correlations among the outgoing quanta over time, or in some structure of quantum gravity we have not fully named yet. So you are not a ghost. You are a set of correlations that may never be reassembled. And if that sounds like a metaphor for memory, it is only because memory is physics happening in wet tissue. Now, to keep the paradox grounded, you should also remember that black holes are not the only places where information feels threatened. Any process involving horizons produces similar puzzles. For example, an accelerating observer in flat space perceives a horizon and a thermal bath. This is the Unruh effect. If you accelerate hard enough, empty space looks warm. Not because it actually is warm in an absolute sense, but because particle content is observer dependent. In quantum field theory, this is a clue that horizons and thermality are deeply connected. So black holes are not unique in principle. They are just the most dramatic because their horizon is not a matter of perspective. It is a global causal boundary. And the thermal radiation is not just for an accelerated observer hovering. It is for a distant observer at rest when you include the curved spacetime. So again, the horizon is where quantum fields and geometry negotiate, and neither side is fully understood. Now, you might want a more tactile sense of what it means for information to be stored on a horizon. Imagine writing a diary, but you are forced to write it on the surface of a balloon. Every time you add more pages, the balloon expands. The diary is not inside. It is on the surface. A black hole's entropy, scaling with area, is like that. The more it eats, the larger the horizon area, the more storage capacity it has, in some sense. But the writing is not in ink. It is in quantum microstates, and the microstates are not readable by ordinary means. So the diary exists, but you cannot open it. You can only weigh the balloon and measure how fast it spins. Congratulations! You have discovered cosmic data privacy. Now, with that in mind, you can consider one more layer of weirdness. The idea that space-time itself might emerge from entanglement. In some approaches to quantum gravity, the connectivity of space-time, the fact that one region is adjacent to another, is related to patterns of entanglement between underlying degrees of freedom. If entanglement builds geometry, then a black hole interior might be understood as a particular pattern of entanglement structure. This is still speculative, but it is one of the ways people try to make the missing pages reappear. There are proposals linking wormholes and entanglement, captured in the phrase ER equals EPR. ER refers to Einstein-Rosen bridges, wormholes. EPR refers to Einstein-Podolsky-Rosen entanglement pairs. The idea is that entanglement and wormholes might be two descriptions of the same underlying connection. If true, then black hole interiors and information escape might be described in a new language, but that language is still being written. So you do not have to memorize it. Just notice the pattern. When people hit the horizon paradox, they suspect the solution is not a tweak. It is a rethinking of what space-time is. And that is the kind of thought that can keep you awake if you let it. But if you hold it gently, it can also become soothing. Because it means your confusion is appropriate. You are not failing to understand a simple thing. You are brushing against an unsolved problem. Now, we can bring you back towards safer ground again, still inside the broader black hole story, but away from the singularity. Let us talk about what you would actually see as you approached and crossed a horizon, because vision is one of the few sensory metaphors your brain trusts. Outside the horizon, light from the universe is bent. You see the star field distort. As you get closer, lensing becomes extreme. Light from behind wraps around. You can see multiple images of the same star. If you could see your own back, you might even see light that left you, orbited, and returned, depending on your proximity and the hole's spin. There is a region called the photon sphere, where light can orbit. For a non-rotating black hole, it is at 1.5 times the Schwarzschild radius. Those orbits are unstable. A slight nudge, and the photon either escapes or plunges. This contributes to the bright ring seen in black hole images, where photons skim around multiple times before escaping. As you cross the horizon, if you are in free fall, local physics remains normal. You do not see a special surface, but your view of the outside universe changes. Light from outside can still enter, the outside can still affect you. The causal barrier is one way. You cannot send out, but you can still receive in. So you could still see the outside universe in a distorted way as you fall. In some descriptions, the outside universe appears to speed up. You might see distant stars age rapidly. In principle, you might see the future of the universe play out above you as you fall inward. In practice, your ability to see that is limited by light intensity, by blue shift, and by the finite time you have before tidal forces destroy you. There is also a danger. Light falling in gets blue shifted in your frame, potentially becoming intense radiation. If you fall into a black hole with background radiation, the cosmic microwave background, starlight, anything, it can be blue shifted as you approach the singularity. So even if the black hole was initially quiet, the interior may not be gentle. The universe outside may become a concentrated beam of high-energy photons in your sky. This is another example of the universe saving its worst details for later. So, the interior is not just darkness. It can be a place where the outside universe is focused and amplified in strange ways. Again, the specifics depend on the black hole type, spin, and your trajectory. But the general message is consistent. You do not get a peaceful day inside. You get a finite interval of increasingly extreme physics. Now, let us widen again, because your fall is only one scale, and black holes operate across scales. There are stellar mass black holes formed from star collapse. There are intermediate mass candidates, perhaps formed by repeated mergers or direct collapse in dense clusters. There are supermassive black holes in galaxies. There may also be primordial black holes, hypothetical objects formed in the early universe from density fluctuations. Primordial black holes, if they exist, could range in mass from tiny to enormous, depending on formation mechanisms. Small primordial black holes would have evaporated by now if Hawking radiation behaves as expected, because smaller means hotter and faster evaporation. But if some formed with larger masses, they could still exist, perhaps contributing to dark matter, though constraints are strong. This matters because it reminds you that black holes are not only endpoints of stars, they are possible fossils of the early universe. And fossils carry information too, in their distribution, their masses, their mergers. Now, speaking of mergers, there is another subtle effect worth mentioning, because it connects to the idea of information in a different way. When black holes merge, the final hole can receive a kick. This is due to asymmetric emission of gravitational waves. If the system radiates momentum unevenly, the remnant recoils. It can be ejected from its host galaxy in extreme cases. So black holes, despite their reputation as immovable pits, can be thrown. They can wander. The universe is not tidy. Now, come back again to the personal, because that is how this story stays intimate. You are still the one who fell. You are still the one who crossed the horizon. And the only reason your fall matters is because it forces you to ask what it means to be describable. When you say you are you mean a stable pattern. A pattern of atoms, yes, but also a pattern of information. A black hole takes patterns and hides them behind a boundary. It forces you to confront the difference between being destroyed and being inaccessible. From the outside, you are inaccessible. From your own frame, you are destroyed. Those two truths coexist without needing to reconcile for any observer. And that is the deeper lesson of relativity in general. Reality is not a single story. It is a set of consistent stories, each tied to an observer's frame, stitched together by invariants. The invariants are what physics trusts: the proper time along your world line, the mass measured at infinity, the area relations, the conservation laws that survive. Your narrative, your subjective experience, is not an invariant. It is still real, but it is not what the equations prioritize. That is why your species invented art, to store what the invariants do not. Now, we have been lingering at the paradox in the interior long enough that you might forget something. The black hole itself, as an object in the universe, is not eternal, even if it lives longer than anything you can reasonably picture. It ends, but the ending is slow, and we are not there yet. We are still at the stage of asking whether the universe keeps a record. So let us stay with the record a bit longer and make it even simpler. There are two broad attitudes. One is that black holes destroy information. They are fundamental erasers. If that is true, then the universe is not strictly reversible in the quantum sense. There is a built-in forgetfulness. The other is that black holes preserve information. They are scramblers, not erasers. If that is true, then the universe remembers everything, but in a form that is practically unrecoverable. Both attitudes are uncomfortable. For the first, you lose a core principle of quantum theory. For the second, you gain a universe that keeps perfect records, which is existentially invasive, even if no one can read them. Most physicists lean toward preservation because too much else depends on unitarity. But the debate is not just preference. It is about consistency across frameworks. And one reason preservation is favored is because in controlled theoretical settings like holographic dualities, information preservation appears required. So the current mood is that information is not lost, but it is hidden and scrambled. If you want a bedtime version, it is this: the universe is not sentimental, but it is thorough. It may not care about you, but it keeps receipts. Now, as you hold that, you can also hold another quiet detail. Even if information is preserved, it might not come out in any recognizable way. Imagine taking a sentence and hashing it with an algorithm, producing a string of symbols. The hash preserves some relationship, but without the key, you cannot reconstruct the original sentence. Hawking radiation could be like that. Information encoded in correlations that are effectively impossible to decode. So the universe remembers, but it does not gossip. That is almost kind. Almost. And speaking of kindness, there is something worse than being forgotten: being remembered incorrectly. If information is scrambled and spread across the horizon, your identity is not preserved as a coherent thing. It is preserved as a distribution of microstates. So, if you were hoping for immortality as a pattern, a black hole offers a very unromantic version. You are not saved. You are stored. Now, keep drifting with that thought, because we are going to pivot soon toward the black hole's own lifespan and how even these dark places fade. But not yet. First, one more subtlety about horizons, because it matters for how you picture the information story. In classical general relativity, the event horizon is a global concept. It is defined by the causal structure of the entire space-time. To know where the event horizon is, you need to know the full future of space-time. You need to know what will happen at late times. That is awkward, because it means the event horizon is not something you can determine locally with a meter. You can determine apparent horizons, trapping horizons, surfaces where outgoing light rays have zero expansion. These are more local, more physically tied to what matter is doing right now. In dynamical situations, like a black hole forming from collapse, horizons can form and evolve. The event horizon can begin forming before the collapsing matter crosses a certain radius. In a global sense, it is as if the horizon anticipates the future, not by magic, but by definition. This is another reason black holes feel like cosmic horror. Their defining boundary is not just a material surface. It is a property of the entire space-time story. So when people talk about information on the horizon, there is subtlety about which horizon and how it behaves in time-dependent situations. But the overall picture remains. There is a boundary beyond which communication outward fails. And that boundary is where the paradox lives. Now, you can let that complexity sink into the background like the hum of a refrigerator in a dark kitchen. Because the next part of this story is slower and, in a way, gentler. Black holes evaporate. And evaporation is not a fall, it is a waiting. But to talk about evaporation properly, you must accept a timescale that makes your brain try to leave the room. You must accept that the universe is very patient. And you, if you are still listening, are patient too, at least for tonight. So, you can hold your position outside the black hole now, at a safe conceptual distance. You can watch it sit there, quiet and heavy. You can watch it as the universe ages around it, stars forming, burning, dying, galaxies colliding, background light thinning. And you can imagine the black hole, not as a monster, but as a bank account of mass, slowly paying out tiny withdrawals of heat, a faint whisper of radiation, so cold for large holes that it is almost meaningless in the present universe. Almost, because eventually, the universe itself cools below that temperature. Eventually, the background becomes colder than the black hole. And then, the black hole is no longer a net absorber. It becomes a net emitter. And then, over times that feel like a joke told by geology, it begins to shrink. And speaking of shrinkage, speaking of slow loss, speaking of the quiet ways the universe takes even the largest things and sandpapers them down into nothing, there is a